Hello, and welcome to this presentation on matrices where we're going to solve two linear simultaneous equations. This presentation does assume you've seen a previous presentation related to an introduction to matrices, as the terminology and procedures in that presentation underpins the work in this presentation. To solve two linear simultaneous equations, we have to first find the inverse of a 2 by 2 matrix. The inverse or reciprocal of a matrix A is denoted by a to the negative 1, such that A multiplied by a to the negative 1 equals the unit matrix, as outlined in a previous presentation. The process of inverting the matrix allows the division in matrices to be undertaken. If three matrices, labelled A, B and X, are such that A multiplied by matrix X is equal to matrix B, then rearranging X is equal to B divided by A. However, as discussed previously, we cannot divide in matrices, so therefore we have to find the inverse of matrix A, the a to the negative 1, and multiply that by matrix B. Note that the inverse matrix, the a to the negative 1, is on the left hand side of the matrix B, as it was initially on the left hand side of matrix X. It is essential to understand this, as from our previous presentation on the introduction to matrices, we noted that matrices are not commutative. In other words, matrix A multiplied by matrix B does not equal to matrix B multiplied by matrix A. Thus, the order in which we multiply the matrices has to be correct. In this case, as the A is in front of the X on the left-hand side of the equation, when we find the inverse on the right-hand side, the a to the negative 1 must be in front of the B. So the inverse of a matrix A must be found before matrix X can be determined. And how to calculate the inverse of a matrix is what we will now review on the following slides in this presentation. Example 4 shows us how to evaluate the inverse of a matrix, and I've broken it into two separate entities. On the left hand side, I'm going to evaluate the inverse matrix using generic algebraic notation, and on the right hand side of example 4 I've used numerical values in the solution to find the inverse. Let's first look at the left hand side of the algebraic solution to find the inverse of a matrix. So given matrix capital A that has elements of A, B, C and D here, to determine the inverse of a matrix we're going to use the following procedure. So looking at the algebraic illustration of the inverse, in step 1 we're going to change the position of elements A and D in the matrix. So here can you see that the A and D elements have been interchanged from that shown in the original matrix A. In step 2 we're going to change the sign of elements B and C only. So here can you see that the sign of element B and the sign of element C has changed. In step 3 we're going to calculate the determinant, often shown by symbol capital delta. Now delta is determined by elements A multiplied by D and subtract from that elements B multiplied by C. So finally, to form the inverse of matrix A, the matrix from step 2 above is now multiplied by the reciprocal of determinant delta. So now we've got a to the negative 1, the inverse of matrix A is 1 upon delta, 1 upon the determinant, and that's multiplied by the elements D, negative B, negative C and A. Let's now revisit example 4, but this time we'll look at a numerical illustration of finding the inverse of matrix A. On the right hand side of example 4, matrix A is now defined with elements of 5, negative 3, negative 2 and 1. So we're going to follow the same procedure as on the left hand side in the algebraic illustration, but we're going to use the numerical values. So in step 1, the position of elements A and D are now to be interchanged. So we now get 1 and 5 here. Notice how the positions have been changed from that given in the question. In step 2, we're now going to change the sign of elements B and C. So these elements here and here have change of sign. They were negative in step 1, so we change those signs to positive in this case in step 2. In step 3, we're going to calculate the determinant, symbol delta here from above. Now, algebraically speaking, that is A multiplied by D. So in this case, there's element A and element D. So A multiplied by D. And we subtract from that elements B multiplied by C. So B multiplied by C are the elements here. Numerically, that is 5 take away 6. So negative 1 is the determinant. So finally, the inverse of matrix A, the A to the negative 1, is written as 1 upon the determinant, so that's 1 upon negative 1 in this case, multiplied by the matrix from step 2, which has elements of 1, 3, 2, 5. And finally, I simplified the A to the negative 1 matrix by dividing every element by the negative 1 determinant. So there's a change of sign for every element in the matrix. And there's my solution for the inverse of matrix A. Here are some tutorial questions related to calculating the determinant delta. From the previous slide, delta of a determinant having elements A, B, C and D is calculated by element A multiplied by D, and then we subtract from that element B multiplied by C. Here are some questions 1 through to 15. I would encourage you to attempt these questions and calculate the determinant. The answers are shown in the square brackets on the right hand side. So just to start the questions for you, for question 11a, to work out the determinant, it would be 2 multiplied by 5, which is 10, and we subtract from that 3 multiplied by 4, which is 12. So 10 take away 12 gives us negative 2. I would encourage you to stop the presentation and attempt these questions. Here are questions 16 through to 20, requiring us to find the inverse of the 2 by 2 matrices specified. So we need to now apply the procedure shown in example 4 on the previous slide. We'll apply the 3-step process to calculating the inverse of a matrix. The answers for the inverse matrices are shown on the right hand side in square brackets. I'd encourage you to stop the presentation and calculate the inverse of these 2 by 2 matrices before proceeding with the presentation. Let's briefly look at determinants involving complex numbers. In previous presentations, we looked at the use of complex numbers to solve various types of problems. Here we're specifically going to look at calculating a determinant that involves complex numbers. So in example 5, we're asked to find the determinant delta of the following matrix having elements of J4, 2 plus J3, 1 minus J5, and J3. Again, for reference, calculate the determinant, it's going to be elements A multiplied by D, and we subtract from that elements B multiplied by C. Here's a solution. So calculate the determinant of the element shown above. It will be J4 multiplied by J3, shown here, and we subtract from that the element 2 plus J3 multiplied by 1 minus J5, so that's shown here. So J4 multiplied by J3 is J squared 12. And we're going to subtract from that the binomial expansion above. So don't forget we're expanding our brackets here. So using my crab claw method, I will expand like this. You may have a different way of expanding your brackets. But expanding, we will get 2 minus J10 plus J3 minus J squared 15. I'll let you check that for yourself. On the next line, I'm replacing the J squared with negative 1. Don't forget from our complex number work, J squared have a value of negative 1. So I'm just simply replacing J squares with that value. So on the next line, we get the change of signs occur because of the negative 1. So change of signs here and here. What I do on the next line is simply add my like terms in the brackets. So 2 add 15 is 17, and negative J10 plus J3 is negative J7. On the next line, I'm just accounting for the negative outside the bracket here, so I will get negative 17 plus J7. Be careful if you double negatives there. That simplifies ultimately to a determinant of negative 29 minus J7. So that's the determinant for example 5. Here are some exercises related to calculating determinants of complex numbers. Exercise 5, solution shown here in the square brackets in factorised form. And exercise 6, again solution shown in the square brackets. I'd encourage you to start the presentation and attempt these exercises. Example 6. We're now going to solve simultaneous equations using matrices. So the two equations given are 5x plus y is equal to 7 and 3x minus 4y is equal to 18. So to solve the simultaneous equations, the first thing we need to do is to create three matrices labelled A, B and C here. So matrix A, this is the matrix of the coefficients associated with the x and the y terms above. So let's consider the coefficients for the first equation, and note that there will be a 1 in front of the y that we don't write, but it's there. So extracting the coefficients for the first equation, 5 for the x and 1 for the y. If we look at the second equation, we've got 3 for the x and negative 4 for the y. So that's the matrix of coefficients. Matrix B is the matrix of the variables. And the variables in this case we can clearly see are x and y. And finally matrix C, this is the matrix of the constants, in other words the right hand side of the equation shown above. So for the first equation the constant is 7 and for the second equation the constant is 18. So now writing the two simultaneous equations given in example 6 in matrix form, we will get matrix A multiplied by matrix B, and that's equal to matrix C. So as the elements for matrix A, that will be 5, 1, 3, negative 4, which we're multiplying by the x and y variables for matrix B, and that's equal to the constant 7 and 18. So now our two simultaneous equations are written in matrix notation. Example 6 continued. We're now going to algebraically rearrange to make the matrix B the subject. So in other words, matrix B is equal to A to the negative 1, that's the inverse of matrix A multiplied by C. And again, it's very important to note that matrix A to the negative 1, the inverse of matrix A, is on the left hand side of matrix C because it's initially on the left hand side of matrix B. Be careful, we must have the correct orientation of the matrices. So in this case we have matrix B as a subject which contains the variables x and y we're trying to find, and on the right hand side we have to find the inverse of matrix A and multiply that by matrix C. So now we've got to find the inverse of matrix A. So this requires our three-step process that we used on example 4 in the previous slide. If you remember the procedure from example 4 for finding the inverse, we interchange elements A and D in the original matrix, and we change the sign of elements B and C in the original matrix. We then work out the determinant, which is elements A multiplied by D, so in this case negative 4 multiplied by 5, and we subtract from that the elements B multiplied by C, so in this case negative 1 multiplied by negative 3. That evaluates for the delta in this case to be negative 23. Be careful if you double negatives in the calculation. So our A to the negative 1 is 1 upon the determinant, so it's 1 upon negative 23, and that's multiplied by the elements in our matrix. So to calculate the unknowns for matrix B, it's going to be the A to the negative 1 multiplied by C. So on the left hand side we've got matrix B, the x and y unknowns, and on the right hand side of the equation we've got the A to the negative 1 multiplied by C. But don't forget from our previous presentation to multiply matrices, we multiply rows by columns. So taking the first row in the inverse matrix, multiply it by the column of matrix C. So that will give us this sum here, negative 4 multiplied by 7 plus the negative 1 multiplied by 18. Be careful of your signs when you're doing calculations. That eventually evaluates to negative 46 for this element. And then multiplying the second row in the inverse matrix by the column matrix C, that will give us this set of calculations here, the negative 3 multiplied by 7 plus the 5 multiplied by 18. simplifies to this and eventually evaluates to the coefficient 69. The final step in the process is to divide each of the elements by the determinant, the negative 23. So in this case, negative 46 divided by negative 23 is positive 2, and 69 divided by negative 23 is negative 3. So we found our solutions now for x and y using matrices. X is equal to 2 in this particular case, and y is equal to negative 3. Here are some tutorial questions related to the solution of linear simultaneous equations using matrices. In question 21, we've got two unknowns, p and q. The equations are already stated in the correct format. We've got the p and q terms on the left-hand side and the constant on the right-hand side. So that's a direct solution as shown in the previous example. Answers are shown in the square brackets. In question 22, make sure you initially rearrange the equations to get the a and b unknowns on the left-hand side and all the constants on the right-hand side. Again, the answers are shown in the square brackets. In question 23, you can consider this in fraction form as written, or if you wanted to, you can multiply the two equations by their respective common denominator to eliminate the fractions. I'll leave that to you to decide. Question 24, make sure you rearrange the equation to get all the constants initially on the right-hand side of the equation. Question 25, again we've got fractions here, I'll let you deal with that. You want to rearrange the equation to get all the x and y terms on the left-hand side, all the constants on the other. Again, in question 26, we've got fractions to deal with. You could, with the first equation, multiply throughout by 6, and that would remove the fractions. And the second equation, you can multiply it by 6, and again, that would remove the fractions should you want to. In all questions, the answers are shown in the square brackets on the right-hand side. I would encourage you to stop the presentation now and undertake these questions. Tutorial questions continued. Questions 27 and 28 are descriptive questions where we need to extract the information from the question, rearrange it in a suitable form. So in both questions 27 and 28, rearrange the equations to get all the unknowns on the left-hand side and the constants on the right-hand side. In question 27, your unknowns are v1 and v2, and in question 28, your unknowns are u and v. Answers again are shown in the square brackets. And here we have further descriptive questions to consider. In question 29, it appears first of all that we have 3 unknowns, but if you read the question carefully, you'll see there's only 2 unknowns. Again, you need to rearrange the equations to get all the unknowns on the left-hand side and all the constants on the right-hand side. In question 29, you could solve for 1 upon u1 and 1 upon v1 using the fraction form if you wanted to. In question 30, you need to read the question very carefully, extract the information, form the simultaneous equations, and then put them into matrix form to find the solution. Again, the answers are shown in square brackets for the unknowns a and b. I would strongly encourage you to stop the presentation and attempt these descriptive questions. They are quite thought-provoking, but they do follow the same procedures for solutions as shown on previous slides. Here is the bibliography used to generate the presentations. Of very good textbooks here, some written specifically for technician engineering students. I hope this presentation has been helpful to you, and thank you for viewing.